Maria. Worked mainly in epistemology of science and philosophical logic. So she interests extends into history of science and non-classical logic. That's very interesting. So her current research focuses on the study of the connections between understanding and the rational use of defective information in science and philosophy. Currently, with Moisés Macia Bustos, she coordinates the Ibero-American Philosophy of Science Seminar. And she will talk on serendipity and ignorance to knowledge and understanding in big data practice.
So thank you very much for staying to this long. I am very happy to be presenting this at this symposium. And okay, so today I'm going to be talking about how to go from serendipity plus ignorance to knowledge and understanding in big data practices. And the question that is going to be at the core of the presentation is how can we make sense of the continued trust placed by scientists in discoveries made by accidents, by serendipity, while also ascribing rationality to them. In particular, in cases in which in big data practices, scientists accidentally arrive at game-changing novel results, but they also irremediably ignore the ways in which these results were actually constructed. In order to do so, today I'm going to try to convince you of three main things. First of all, when you combine serendipity and certain types of epistemic opacity from big data practices, this challenges our ability of achieve certain kind of understanding, of any kind of scientific understanding of the things that we are working with. The second thing is that in big data practices, what is most characteristic is the type of ignorance that we can find, and this type of ignorance is ignorance of theoretical structure with reliable consequences. And finally, the third thing that I'm going to try to argue for is that the reliability of serendipitous discoveries warrants the achievement of knowledge and understanding in these cases. And I'm going to try to focus on cases in which the epistemic agents are the center of our study, in a sense. So usually you can find a lot of epistemological approaches to data science that are focusing on the methodological grounds of this data science, but not necessarily on which are the outcomes for the epistemic agents in particular. So this is going to be the main object of the study today. So the plan is going to be the following. First, I'm going to talk a bit about some preliminaries on serendipity and ignorance. Then I'm going to move to talk about epistemic opacity in big data practices and to say how these epistemic opacities might challenge our achievement of understanding. And then I'm going to move to describe what ignorance of theoretical structure is. And then I'm going to say something about the reliability of serendipity. So first of all, data, let's take data to be something that anything can be soundly recorded in a relational database, respecting a semantic and pragmatic requirements. Big data is the field that concerns ways to work with data sets whose size is beyond the ability of typical databases, software tools to capture, analyze, store, and manage. And as the other two participants of the workshop have already said before, it has at least 5 characteristics, which are often called V characteristics, which are going to be volume, velocity, variety, veracity, and value. And so an important first reflection is that usually big data does not only indicate the amount of data that is managed, but from an epistemological and methodological point of view, the range of computational methods used to work with such data. And something important about big data is that often it comes with good results. So different scientific disciplines that have been benefited from the emergence of big data and data science, and this has happened for science such as astronomy, geology, climatology, biology, among others. And they get better results, better predictions, more accurate predictions, more accurate descriptions, visual representations of phenomena that they couldn't have access to before, and so on and so forth. And so, in particular, in the case of sciences such as observational cosmology, big data has allowed us to see some things that were initially inaccessible to us. So observational cosmology is supposed to provide us with observations about celestial bodies, but there are some celestial bodies that are very far away from us, that we wouldn't be able to reach visually with a simple telescope or with our naked eye, right? So big data practices has brought us closer to this phenomenon. And so in the case of serendipity, let's think of serendipity as the category used to describe discoveries that occur at the intersection of chance and wisdom. To the words inventor, Horace, it describes discoveries made by accident and sagacity of things and were not quest for of. And so serendipity is often related to at least three different and related phenomena. So the first of them is abduction, which is an inferential phenomena, and consists in saying, oh, I often try to go back and explain how I got here, mostly motivated by the anomalous character of the phenomena that is discovered through serendipity. So usually we discover a phenomenon, or we see or we entail something that is anomalous in the sense of either it lacks of explanation or it was unpredicted. The theory didn't say anything about this, or our knowledge, background knowledge didn't tell us that this was coming. And it's surprising in this sense, in the sense that it is anomalous. And it has features that are also reinforcing this surprising character. For instance, the degree of accuracy. So this is so novel and it's so accurate that it has to have an explanation, and that's where abduction comes in, to try us to provide us with an explanation of how this was discovered, and which is the value for our current enterprise. And so serendipity has this game-changing character, which is very characteristic of why serendipity is so important in the sciences. So, and it comes with the possibility of interpreting and explaining post hoc the discovery, how we got it there, and also what does the discovery mean for our current practice or current enterprise. And so it is not something new that serendipity has been related to ignorance. So for instance, the first type of ignorance that we can find when we have serendipitous discoveries is the fact that we don't know where we are going. So, and we arrived to that point very surprisingly, and we don't necessarily know which was the process at the very beginning that we were going to follow, or what we were going to find, or what was going to be the value of this thing that we were going to find. So this connection is not novel at all, and it's very common in the literature of serendipity in the sciences. But also we have this intuition, which is very traditional in a sense, that we survive serendipity. So if scientific enterprise is actually a rational enterprise, to arrive to good results by purely luck or by chance doesn't seem too rational. So while many of the discoveries and the important discoveries that we have gotten in the sciences have been achieved through serendipity, we think that we have the epistemic obligation of providing an explanation of an rational reconstruction of how these discoveries were made in such a way that we can assure that science is rational, at least in the post hoc explanations. And so, but what happens if this thing, the possibility of interpreting and explaining how we arrive to a particular discovery, is not possible for us? And this is the main question that I will tackle here. So when we are trying to explain which are the epistemic benefits of scientific inquiry, we shouldn't stay only with the fact that we want knowledge about the world, for instance, in the case of the empirical sciences. But we also have to say that that we want explanations of how we achieve this world, this knowledge. Basically, because we want to understand two things: what science is doing and how whatever science is providing us with relates to the, for instance, the actual world or the domain of scientific study. And this relation, this more general relation or picture, is often what we call scientific understanding. And understanding consists of knowledge about relations of dependence. When one understands something, one can make all kinds of correct inference about it. So at this point, we can say the following about the scientific picture in general. We can reach certain discoveries, maybe the most important, maybe the most novel, through serendipity. But then we have to search for a type of knowledge about how these discoveries were made, how they impact our current scientific enterprise, what do they mean, what do they refer to, and so on. And once we achieve all these types of knowledge, it seems that we get a more comprehensive picture of both the science and the world that we are studying. So this is the way in which serendipity, knowledge, and scientific understanding usually should relate according to a traditional view. You may come from serendipity, but you have to go to knowledge. And once you are very successful at achieving certain type of knowledge, then you can move to understand. And a particular thing about understanding is that in the literature, it is often regarded as factive. This is the content of understanding, often is thought to be true. So we can understand only things that are true. We can have the impression of understanding things such as lies, very systematic lies, things such as conspiracy theories that are not necessarily all things true. But that's only the impression, that's a false impression. And so legitimate understanding, which is the most valuable asset of scientific enterprise, can be achieved only when the content of understanding contains only true propositions. But as we were discussing in the first talk with Giovanni, maybe in big data practices, this is not so clear how we can get all true propositions and then to say, oh, I got understanding, this very strong factive understanding of the phenomena that I am studying. And so the view that I'm going to hold here is one that is called non-factivism, which says that sometimes we can achieve understanding of things that we don't know whether they are true or false, and that are very likely to be false, or at least not true. You could say they are vague, they are imprecise, you have all these fuzzy values in between, and so they are not completely true, but you can still say that you achieve legitimate understanding. Furthermore, so the incorporation of big data into the empirical sciences has modified the ways in which scientific knowledge was pursued and scientific methodology was followed. So this is not something new, but we want to ask how this change into big data practices has modified or has affected our epistemic processes for the achievement of knowledge and understanding, and especially from moving from serendipity to explanatory knowledge about how these serendipitous processes went on, or how certain novel products were constructed, to the achievement of scientific understanding. And so first, we can move. So we have a picture now. If we grant that scientific practice has changed thanks to big data incorporation, then we have a challenge of explaining how this understanding can be achieved, or this knowledge can be achieved. And scientists have to explain how they can move from serendipitous discovery to something more solid or stronger. And only by providing this explanation, we can explain that they are being rational when trusting the outcomes of these big data processes. And so this is going to be the challenge. To choose to explain how scientists are in facing a dilemma. Either they choose between rejecting the evidential role that these outputs constructed by serendipity in big data might play, or at risk of being irrational, they rely on them even when ignoring how they come from and how they were obtained. And so what do I mean when I say scientists, when incorporating big data into their practices, might be ignorant of the ways in which the products are obtained? What I have in mind is that usually science is epistemic opaque for many of us. What is epistemic opaque means? Well, a process is epistemic opaque if we cannot explain which are the steps that get you from one point to another, in particular, which are the relevant steps that take you from the initial stage to an important outcome. So we usually are not capable of explaining how scientists go from certain types of information about the world to predictions or explanations or even theories. So that shouldn't surprise us. But the problem is that when scientists are very, very ignorant or find their own activity to be epistemic opaque for them, it's not clear how they are going to be able to explain the rationality behind the things that they are doing. And so in that sense, the scientists' lack of transparency regarding privileged purposes and uses of data is one of the cases in which one can say that we have epistemological opaqueness. So there is one, and there is another, which is going to be the heavily reliance on correlations associated to big data practices and the epistemic opacity that surrounds the results of big data. So let's go up to the first. The first one is very intuitive. We usually capture more information that we can manage, but also we capture information just in the sense for the fun of it. And so we have to decide which are going to be the purposes and which are going to be the values that we assign to this data. And so we usually ignore that. But then let's move to the two other epistemological challenges of big data practices. And the first one being the heavy reliance of correlations. So correlations are the statistical relationship between two data values and are notoriously useful as heuristics devices within the sciences. So we usually are happy when we get certain correlations, but traditionally, correlations are not informative enough to be considered to suffice for explanation. And we usually think that science wants to provide us with explanations. So if big data practices are providing us with more correlations than explanations, or with only correlations, we are facing the challenge of explaining how we can rely on these things to provide us scientific knowledge about everything, about the world, about the theories, about even how this data relates to one another, and so on. And so, but yet, so if explanations cannot be obtained, no understanding is achieved in the cases in which we associate understanding to an explanatory type of epistemological character. So if big data practices provides us with a lot of correlations, but no explanations, then, I mean, we can say we get some information about the world, like some propositions that might be true, but we cannot move there to explanatory knowledge, and then we cannot move to a way in which we say, oh, this is the way that all these things hold together, and that's the way we understand the world. Nonetheless, the value of these correlations has been changed by the incorporation of big data into the sciences. The correlations might not tell us precisely why something is happening, but they alert us that something is happening. And so for the cases in which the phenomena, for instance, was very far away from us, that we couldn't even say whether something was true or not, these correlations are informing us about certain facts. Oh, this is occurring. Well, this other thing is occurring at the same time. So we might not have explanations, but we have new information that we wouldn't have gotten without big data practices. That's the crucial part. And this is a new way of understanding correlations, making them fundamental for scientific development in the sense that only through them scientists can obtain novel, comprehensive descriptions of the world. Now, the other epistemological challenges. are going to be constrained by epistemic opacity of big data processes and products. So a process is epistemically opaque, as I was saying, to a cognitive agent at a time t, just in case this agent does not know at all all the epistemically relevant elements of the processes. Contrary to opaqueness, you can find transparency. And transparency is often achieved when an agent can know when a step is produced in the procedure is relevant. And this is what we call weak transparency, when they only know whether something is relevant or not, as well as when it is not. So the combination of knowing when a step in a procedure is relevant and knowing when it is not is what we call a strong transparency. And as you can imagine, we are a lot of processes for us in our daily life are weak transparent. So we can know whether it is useful for me to walk to in certain way if I want to read something, but not necessarily I have access or I have explored the options of when it is not going to be useful to move in a certain way. So a strong transparency is often more challenging to be obtained for epistemic agents. But in the cases of big data practices, given our physical constraints, there are certain phenomena that we would not be able to access without the help of big data. As I said, the behavior of celestial bodies, such as distant galaxies. In addition, given human cognitive limitations, the implementation of big data in the sciences comes with the need of computational methods that aid scientists to compute information that humans would not be able to compute by themselves. Unfortunately, these methods are not always epistemically transparent to human agents. In particular, these methods sometimes require the implementation of inferential procedures that are essentially opaque to us and the scientists. And when you add to big data practices things such as machine learning algorithms, there are going to be at least 3 types of epistemological opaqueness that we are going to be dealing with. Algorithm functional opacity, procedural opacity, and run opacity. The first one occurs when at a certain time it is impossible for an epistemic agent to know the high level of logical rules according to which the system will transform, given an input into an output. So this is the most general type of epistemic opacity. If you don't know, if you have not access to this, it is very likely that you are going to have epistemic troubles at the lower levels. The second type of epistemological opacity that we are dealing with in big data practices when adding machine learning algorithms is procedural opacity. This takes place when at a certain time, an epistemic agent knows the algorithm that a specific code realizes, but still has no epistemic access to know how this realization occurs. And this is very common because machine learning algorithms, thanks to deep learning, are going to be modifying themselves without our inputs, without us tracking them very sharply, for instance. This type of epistemic opacity seems to require that agents are unable to decompose each part of the inferential procedures that constrain the model in question. This type of epistemic opacity becomes even more problematic because it affects the access to and legitimacy of the links between the particular program and its success within a particular domain of application. And there is a latter type of epistemic opacity, which is run opacity, and is the most concrete type. It occurs when at a certain time, the agent ignores a program as it was run in a particular instance. This ignorance might involve either the hardware or the input data used. So this is the most refined type of epistemic opacity that we are going to find. So even if you know all the other things, if you know the algorithm, if you know the procedure, there are going to be software and hardware types of constraints that might change your access to how the products are obtained. You might not know how to run certain thing in a particular computer might affect the result. or you might not know how a particular type of hardware might change the ways in which certain data is filtered and so on. And so considering these three types of epistemic opacities, we have the following challenge. So the combination of these types of epistemic opacity might make scientists skeptical about the reliability of the process and the products of at least some computational methods in big data practice. So you can say, okay, that's fine because I often have epistemic access to the things that I'm doing when implementing big data into my scientific discipline. But those things that you have access to are not going to be the problem. The problem with your rationality are the things that you are relying on, and you have not epistemic access, and you will not have any epistemic access to that. So the fact that scientists might not be able to decompose the steps through which some outputs were obtained leaves them lacking explanations for the legitimacy of such outputs. So if we want to be reliable about how scientific knowledge is constructed, then the knowledge of how these processes are followed, or which are the processes that are followed, seems very valuable for having the justification for our knowledge. So if we don't have that, we might not even have any type of knowledge when using big data into the sciences and having these epistemic opacities undergrounding the scientific endeavor. So we have said when we consider the correlations problem, that this might undermine the achievement of understanding in cases in which we relate understanding to explanation. But let's say we don't say so. We say that understanding is independent from explanation, that I can achieve certain understanding even if I cannot explain the phenomenon in detail. It doesn't matter, because this epistemic opacity seems to undermine the achievement of knowledge. So if I cannot say how I am justified for trusting this information, if I cannot be able to provide a strong justification for the veracity or the truth of this particular outcome, then it seems that there is going to be an element lacking from knowledge. And so knowledge is nowhere to be reached in these cases. But what is really happening, and how could we overcome it? So when knowledge is not achieved, we usually say, oh, what is happening here is a certain type of ignorance. But the question is, which type of ignorance? So when we don't know, for instance, the value of the data, we say we ignore the specifics of the domains of applications. We don't know which are the intended purposes for gathering all this data, or which are the intended domains of application, or which are the privileged purposes and interpretations of this data. When we say that we use correlations and that we cannot have causal explanations, what we are ignoring are causal links. What we have is a type of explanatory ignorance. When we are dealing with epistemic opacity at the level of products, how these products are constructed, should we rely on them as true or as strong observation outcomes, or only as, for instance, hypothetical models, how these things were constructed, which were the underlying processes? What we seem to be ignoring is something about the facts in the case of the products. Are these outcomes describing actual facts? Or are they just, as I said, hypothetical results or abstractions or whatever? And what we seem to be ignoring at the level of processes is, well, procedural ignorance, what seems to be undermining our achievement of this type of knowledge. And what happens when we don't find understanding? Oh, well, we say we at least have this explanatory ignorance. And when we deal with this large amounts of information, we say, oh, I don't know whether it is true or not. As I said, we often relate this to factual ignorance, ignoring whether this is a fact or not. And when we don't have epistemic access to the objects of a study, either because they are very far away for instance, such as galaxies, or because they are very diverse and microscopic and so on, as the case of genetics, or because they are everywhere and very well spread, as the case of ecology and birds and so on. What we seem to be ignoring is objectual ignorance. So at least at this superficial level, it seems that ignorance is surrounding a lot of our big data practices. But is there any type of ignorance that is underlying all these other types? And what I think is that what is at the basis is that we ignore how all these things fit together, how instruments fit together, how machine implementation fits together with the instruments, the theories, the empirical inputs that we get, the data filtering strategies, the community inputs, as well as other elements that are going to be part of the processes of getting these novel results in big data practices. And so in these cases, apart from ignoring all these other things, which are facts, procedures, explanations, what we are actually ignoring are these connections that help us to move from a particular input to another input and then to an output.
5 minutes, Maria.
Yes, thank you. From inputs to certain outcomes that we consider to be novel. So what I used to call this thing is ignorance of theoretical structure. What we are lacking of is knowledge of the relevant inference patterns that scientific theories allow for, or in this case that the data sets allow for. And so when one ignores that, something that we cannot do is to determine which are the inferences that are going to be followed. And therefore, we have trouble at determining whether something is true within the theory or within the data set, considering its own constraints. But something very interesting about the types of ignorance that we can find in big data practices is that they are reliable. The outcomes, even if we ignore how they were produced, they are reliable. How do you know that? It often comes that the outcomes obtained through big data practices are novel in the field, are empirically adequate, are fruitful. The outputs seem to be crucial for the development of related research programs in the discipline, or holds a possible evidential relation within a model or a theory in the discipline, even if it was not initially intended. And so how all these things come together when talking about serendipity. And what seems to me that is happening here is that, first of all, this reliability of the products of big data entail or show to possess a game-changing character. The fact that we don't trust all big data outcomes, but we trust the most novel or the most explanatory of the most revealing ones, when we don't have epistemic access to the processes through which they were constructed, it's related to the role that they play in the discipline, which is going to be game-changing. And so how do we know that? Because we usually get something that is objectual knowledge, thanks to big data. We cannot explain how these propositions, these predictions, these descriptions are obtained, but we know that now we have epistemic access, reliable epistemic access to a particular object. In the case of galaxies, for instance, we cannot know how all these images are necessarily integrated, but what we know is that they are constrained in such a way that it is very likely that they are accurate representations of how the galaxies look like, how the black holes look like, and so on. And once we get that, once we get this objectual knowledge, what often happens is that now we know how the world can be constrained. We might not know necessarily which are going to be the consequences of having this object as the way it is. But now we know how it might relate, for instance, a particular characterization of a specific galaxy, how it might relate to other things that we have surrounding the domain. The behavior of other celestial bodies, things such as dark matter. Is it very likely to be true, the hypothesis of dark matter, or isn't it, and so on. And so what seems to happen once we get these novel outcomes is that now we have less moves that we can do, but we still don't know whether necessarily these are accurate or true representations of the world. And the type of understanding that we might gain once we accept all this, what I have been saying, is modal understanding. One has some modal understanding of something if and only if knows how to navigate some of the possibility space associated to that phenomenon. So in the case of big data practices, to achieve modal understanding of the behavior of novel objects in established theoretical domain would be able to determine the set of possible words that correspond to the generic structural relations that are grounded in the data sets. In the case of big data practices, to achieve modal understanding of the behavior of novel objects in an established theoretical domain would be to determine the sets of possible words that correspond to the generic structure of these objects that we have identified. And let's move to serendipity. What happens with serendipity and this modal understanding and this objectual knowledge? So usually we associate, as I said, serendipity to abduction, anomalous discoveries, and surprising discoveries. And what often happens is that when you get these results are, first of all, are phenomena that not necessarily have a previous explanation. In the case of the bullet cluster, for instance, is this image, and the bullet cluster are two galaxies colliding. And what we can say from having a picture of it is that maybe it indicates the presence of dark matter, now that we have access to that. But we are not sure about whether dark matter is actually part of the explanation of how the bullet cluster exists. But we also find the accuracy of the images, the results, and the descriptions that we get through big data practices very surprising. And in the case of images such as the bullet cluster in cosmology, they are very game-changing in the scientific disciplines. And so we usually, as I said, tend to believe that serendipity and epistemic opacity would challenge our understanding. And well, this is true, might challenge our understanding in the sense of factive understanding. We can still achieve something. We can achieve modal understanding of how the world works. And maybe we cannot reconstruct by abduction the processes through which certain outputs are obtained. But what we can reconstruct by abduction is the possible explanations that we have of this phenomena that we have reached thanks to big data. And these possible explanations are going to be in a particular logical space, constrained by the factivity of the phenomena that is described through our new discoveries. And so the reliability of serendipitous discoveries in this case warrants the achievement of knowledge and understanding. This is only when we have outcomes that, even if we cannot explain how they are obtained, and we can never explain such thing, we can say that they are valuable, they are fruitful, they are novel, they seem to be accurate, consider all the knowledge that we have about that particular domain, and they are also going to be very game-changing in the discipline. And that said, I just wanted to say that maybe what is, if we pay attention to the individual agents in these cases, what we have to provide a fine-grained analysis of is the notion of serendipity in the cases of big data practices in which we have no clear epistemic access, or we will never be able to have epistemic access through the processes in which they are constructed, because not all of things that we are ignoring are going to be serendipitous discoveries, even if we ignore the processes and we we consider them to be very novel or game-changing. So that's one of the ideas that I had, and that maybe in these cases, in big data implementations in the sciences, we have a novel type of scientific activity in which serendipity might play an intentionally crucial role, highly important role, versus the intuition that we have to survive serendipity. Because now we are in such a position in which maybe we have more serendipitous phenomenon, and maybe the same will happen as happened with correlations. Maybe we will find a new scientific methodology at the level of epistemology to value serendipitous discoveries in big data. And thank you.